Welcome back to ECE 442-542. This short segment, I hope it's short, is to help you with homework assignment number 6. And the goals are maybe not to individually look at each problem, but to maybe give you a little bit more overview so that you can approach each problem effectively or more efficiently. And I've organized this piece or this help piece in the following way or with the following goals. First, we'll talk about open loop poles and zeros versus closed loop poles and zeros, making sure the notation or the terminology is clear. And those are actually then connected because of the root locus. The root locus actually is this collection of points that shows us where our closed loop poles can live for a particular value of gain k. And those are the red branches in our z-plane. We'll talk about the root locus giving us that connection between the open loop poles and zeros and the closed loop poles and zeros. We'll then talk about, via some examples, how do we find this range of k for stability. And it's not just always looking at z equal 1 or z equal minus 1. There might be some other situations we have to keep track of, and that's what we'll try to make clear. And the other part that I want to talk about in this segment is the performance of closed loop systems, and that is really going to be finding from the poles, the dominant poles, what are the settling time, percent overshoot, and peak time values. And as I hope you'll start to become clear with, is if you simply have a real pole that is dominating your closed loop behavior, that's not going to give you any percent overshoot or peak time. That's going to now just concern you with the settling time, and the percent overshoot will be 0 and the peak time will be 0. It's only when you have complex poles that we have this potential for finding a settling time, percent overshoot, and a peak time, all three at the same time, or for that particular dominant set of closed loop poles. Then I'll have an additional piece, another segment that should help you, I hope, with homework number 6, which is really problem 5 in problem set number 6, and that's dealing with a special case or a special geometrical distribution of 2 poles and a 0, and how can we quickly sketch the root locus for that. So that will be an additional set of a video and notes. What I want to do now is talk about open loop poles and zeros versus closed loop poles and zeros. The notation, we might have a controller, C of Z, and a plant, G of Z, and I've simply put in some suggestive pole and zero factors into those 2 different transfer function blocks, and they're interconnected on our classical feedback, unity output feedback configuration, where the controller and the plant are in the forward path of that block diagram. For our discussion purposes, we really like to reorganize that controller plant and push everything into, we'll call it a G bar of Z, a transfer function, and isolate the gain K in front of all of that. And now we can talk about K G bar, but G bar now is going to pull in all the zero factors and the pole factors that might be associated with the controller, and it also incorporates the zero and pole factors from the plant. But once we have that, then we can establish the notation that we have for G bar. We're going to say its numerator is going to be labeled as N of Z, and that will consist then, if we factor it, in our zero factors, and D of Z is the denominator factors, or the denominator polynomial, which contains the denominator factors of G bar of Z. And when we speak of open loop versus closed loop, What we're really meaning is in the open loop, we're disconnecting the feedback path. That's what we mean by the open loop system or the open loop transfer function. And when we now refer to the open loop zeros, those are going to be the roots or the values of z that cause the numerator of g bar of z, which we're labeling as n of z, to vanish or equal 0. And the open loop poles are the values in the denominator of g bar of z that cause the denominator polynomial d of z to vanish. In our notation, then the open loop poles are the values of z that cause d of z to vanish, or those are P1, P2, P3, and P4. And those could be complex, and we'll keep everything as complex conjugates, meaning we're going to be dealing with real coefficients in our numerators and denominators. But the open loop poles are the values of z that cause d of z, where d of z is defined to be the denominator polynomial of g bar of z, and the open loop zeros are the values of z that cause n of z to vanish, or in our notation, the z1, z2, and z3. Again, some of those z's might correspond to the controller factor, zero factor, or the plant zero factor, but we're lumping those all into one transfer function, which we will call g bar. And I have this alpha, which could have been a gain in our plant, and that's now some fixed constant, and k is what we will adjust to manipulate the dynamic behavior of our closed loop system. Those are the open loop. When we have the feedback path disconnected, then the only path from the reference input R to the output Y is that forward path. There's no feedback. That's what we mean by open loop. If we close the loop, then we bring or we reintroduce that feedback path, the negative unity output feedback, and with closed loop, we can now compute this closed loop transfer function T sub c of z, which is then the transfer function between the reference input R and the output Y with feedback. And we've derived that many, many times. That's kg bar over 1 plus kg bar. In terms of the notation that we've now used to parameterize g bar, we now have T sub c of z, and let's just push that all through. We cancel the common denominators in those numerator and denominator expression, and we end up now with a polynomial in the numerator of T sub c of z. And you'll see that that's simply consistent with the open loop zero polynomial, but we'll call that now also the closed loop zero polynomial, or that's now n of z, and the closed loop poles are going to be influenced by this interconnected combination of the open loop poles d of z plus k, the gain that we're adjusting, times the open loop zero polynomial n of z. And now the values of z that cause that expression to vanish will be our closed loop poles in our system. And in fact, the root locus now is going to show us these red branches that we have in our z-plane. That's going to be this locus of points in the complex plane that corresponds to all the possible values of z that might cause that combination d of z plus k n of z to equal 0, or to be closed loop poles. And we will generate those red branches by allowing k to be adjusted. That's our knob. We're allowing k to be adjusted from 0 all the way up to infinity. That's just stating it another way. Our root locus now are the values of z that satisfy that equation, d plus k n of z. D are our open loop poles, n are our open loop zeros. The d plus k n of z give us the closed loop poles. Now, if we have our denominator polynomial of the closed loop system being d of z plus k n of z, and we're setting that equal to 0, that's equivalent to dividing both sides through by the original d of z polynomial, leaving us with 1 plus k n of z d of z, or that's now this classical 1 plus k g bar of z equaling 0 that we continue to use, but that's now why we use that formula, and we can now derive our root locus rules from that by solving for k g bar of z and setting that equal to -1. That gives us now our magnitude condition and our phase condition. That's where all of those root locus rules come from. And you can hopefully now see that the root locus starts with the open loop poles and zeros, n of z and d of z. That's those x's and o's that we put down into the z-plane. And then we sketch all the possible values of z that could satisfy that equation, d plus k n of z. Those are the red branches in the complex plane. And what we want is to shape those red branches by the choice of our controller, or with the combination of plant and controller, and that's where the design comes into play. We want to eventually be able to adjust our controller poles and zero factors to maybe modify the branches so that they move through the z-plane in a manner that gives us the behavior or the dominant pole locations that we would like. Let's now talk about the range of k for stability. And here we're going to use the root locus to guide our analysis. And by that I mean, if we simply, in this particular sketch, we only have one real pole, we know that the root locus, which is the possible closed loop poles that we could create by adjusting the parameter gain k from 0 to infinity. At 0, it's at that pole location, and as we increase the k, the pole, the closed loop pole, will eventually start to go inside the unit circle. That's what I'm going to be using this yellow highlight for. That's supposed to be a nice circle. This will now give us some k value. Let's say that's k1, and that will put us right on the boundary of stability. We continue to increase the gain k until we get to this particular location, k sub 2, which is now going to give us the gain value that would put us outside the unit circle, or be the upper limit in our stability consideration. So in this case, our k for stability would live between k1 and k sub 2, and we could find that if we use the magnitude condition. In this case, we have our k, let me change pen color, we would have something like k over z minus, let's just say that's at a. And we know that by the magnitude condition, that's equal to 1, so that now k is equal to z minus a, so that we would be evaluating k at the triangle. So now we would say z minus a with z equal to 1. That will give us k sub 1, and k sub 2 in our case will be k, that expression, k equal to the magnitude of z minus a. So let me just go ahead and write that down. That would now be when we evaluate the k expression with z equal to -1, and that will now lead us to k sub 2. Another possibility for a range of k might be where the pole is now initially inside the unit circle. Our root locus sketch is still now all this real axis segment that has the pole lying to its right. Again, we're assuming a positive gain value, or a positive value for our gain k. And now, at the lower limit, k equal to 0, we're obviously stable, and we would now be interested in when do we get to this particular location. So again, if this particular pole is at a, we still have our transfer function and gain looking something like that, so that the magnitude condition we would now be saying, oh, at k equal to 0, we're stable because we're inside the unit circle. Our upper limit, which we might call now k sub 2, is going to be when z is equal to -1, and we would evaluate that so that now k for stability would be between 0 and k sub 2. Now, if we have it a little bit more of a challenge, if we now have two poles, well, we know what the root locus of that looks like. We now know that we still have two branches, even though they're on the same real line segment. They meet, it's just two real poles. They meet exactly in the middle, and now they move at angles of plus and minus 90 degrees off to the two zeros at infinity. Here for stability, we're actually wanting to, at 0 for a gain, we're obviously inside the unit circle, but now what we would be interested in is at what gain do we make it to those triangle locations, and because of the symmetry, when we're at the upper limit in the first quadrant, that will be the same k value to get us to the lower limit. And if we now could calculate the gain k, again, use your magnitude formula, you can hopefully find that particular pole location. In this case, it might be z is equal to, let's say, a plus jb. A would be the, if this is now P1 and this is P sub 2, you know that actually A is halfway between P1 and P2 because of the symmetry and the two-pole behavior. You now know what A is if you have P1 and P2 given. You also know that at this particular location for the triangle, the magnitude of Z is equal to 1, and that now says that you have this a squared plus b squared square root equaling 1, and you can now square both sides and you can solve for b. Once you have that location for this triangle location, now you can plug in your value for k or use your magnitude condition and your expression for k, and let's just say that that's something like this, and now you would evaluate that at z equal to z delta, and you've now computed a and b. You could now find the upper limit, so let's say that that's ku. The lower limit would be 0, and for stability in this case, we now know that k is between k, or 0, and k sub u. We could also have another picture, and all of this now is concerned with the relative locations of these poles relative to the unit circle. Again, if this is P1 and P2, we know our root locus diagram looks structurally just like it did in the last one. It's just now we're not starting with a stable system to begin with because P sub 2 is outside the unit circle. Meaning now we would have to at least crank up our gain until we made it to the triangle. Then we would go to the breakaway point, we would break away, and then we would want to know what's the gain to get us to that square location. And in this case, our gain for stability would be k is bounded on the low side by the k to get us to the triangle, and on the upper side it's bounded by the gain to get us to our square. And again, we could find this location for this pole. We could say that that's, z square is now going to be some a plus jb, and we know it's on the unit circle, so we know the magnitude. We can find the a value again because it's halfway between P1 and P2, and at this point, we know that z triangle is equal to 1. So those are the values of z that you could plug into your formula for k that's derived from the magnitude condition and find your stability range for stability in this, or values of gain k for stability in that configuration of pole pattern. Another possibility might be here, where now you have, again, these two, the one on the right, the branch goes to the left, the one on the left, the branch goes to the right, and maybe by the relationships of these. Now maybe you have a gain to get you to the triangle, but that might not get that pole on the left side yet inside the unit circle. So now you might have to go to the square, and that now might put you maybe here, and then you know your lower limit on k is determined by that square's value, and your upper limit would be the gain to get you to this, let's say now this diamond location, so that the upper limit would be the diamond. And you would now have to evaluate this. You would evaluate with z equal to -1. The value at z equal 1 maybe didn't get you in both branches simultaneously inside the unit circle. And this now you might now say, okay, what is my value? And again, you could find a, because that's halfway between P1 and P2, and you could solve for b based on the fact that a squared plus b squared, that magnitude is equal to 1. Here's another pole pattern. Now we're introducing a 0, but you could use the rules, the rule number 1 or 2, where we now know which segments on the real line correspond to the root locus. These two now will approach each other. They will break away. Maybe they break away here. And we will now, although that's not very well drawn, this is supposed to be a circle with this breakaway point. You would now have to find that breakaway point, and that's not going to be exactly at the center, the algebraic center of those two poles. It will actually be the geometric mean of distances, and we'll talk about that in the subsequent little video. But you would now find that breakaway point, and the first time that you would have stability is when you would now hit these complex conjugate triangles. You would then keep moving around, and eventually then you would have an upper limit based on that triangle. And so in this particular pattern, your k for stability, the lower limit would be the triangle, and the upper limit would be the diamond, where the diamond now is found with z equal to -1. You can see that whatever happened here, let's make that a cloud, at z equal to 1, that may actually not give us stability because both poles are not simultaneously inside the unit circle, or both branches of our root locus are not simultaneously inside the unit circle. And you would now again use this relationship that we have been talking about. This is now a plus jb. You know that that's a distance of 1 away, so you know that this distance is of 1. This distance right here, you know because of the zeros location, and the other part of our triangle that I'm trying to construct is actually the radial distance, where the radius of this circle, so this is a very poorly drawn sketch, but this radius is now going to be the radius of that circle that defines the root locus. And now we have that triangle in there, and if you wanted to, you could use the law of cosines to find the angle that that 0 makes with the triangle location, and that might then help you determine a and b. But it's maybe easier to use the formula for the characteristic polynomial of the closed loop system in terms of k, and the fact that that triangle location, z triangle, is a plus jb and has a magnitude of 1. Another possibility, although it's exactly the same structure as what this one was here, is the root locus. Again, the real line segments I'm now showing these will break away. They will break away at the geometric mean. Then there's a circle that's created, and the radius of that circle is right there, so that this particular point I'll say is z breakaway, and that's now, let's say that that's at a value z plus the radius, and this reentry point, which is the relative minimum, will be z reentry, which is now z minus the radius. And in this case, again, you would be trying to find this value to get you inside. So now you're definitely not stable until you reach the triangle, and then you might be stable until you crank up the gain to get you to that particular box location. Again, your range of k, in this way that I've diagrammed it out, k would now have an upper limit defined by what k was at -1, and a lower limit for stability, what k is to get you to that triangle location. Another possibility would be this particular pattern. We don't have a breakaway, but we do have a reentry, and that reentry, again, would be, if this is now z, would be z minus dr radius. So if you now know where this pole is, P1, and you know the location z, you can find that distance as P1 minus z, and you now have the radius. You can calculate the reentry point, and now you're again looking for the value of gain to get you to that particular point, or the triangle location, and then the box location, or the square, will be your upper limit on the stability for k. So k now again would be bounded between the triangle and the square. If we go a little bit more complicated relative to pole zero patterns, suppose now we have 3 poles. Again, it should be pretty clean in terms of finding the real line segments that belong on the root locus. Now we would need to make sure that what is the gain to get us to that location. Hopefully, then that gain will be to the left of the breakaway. That's obvious. But now this pole hopefully will stay inside the unit circle, and you still have a little bit of potential for keeping the system stable. Now let's say that you have the square there, and it might be that these squares are here. Then you're still stable, and then maybe to get to the cloud, maybe that puts you here. And it might be that that square actually is still inside the unit circle on the left, and the cloud might also still be inside the unit circle when we push on the right-hand side through the gain to get us to the unit circle there. So it's going to depend on the relative values of k and where your closed loop poles are. The way that I've sketched it here, k for stability would be lower bounded by the triangle location, and it would be upper bounded by the square. But depending on the relative locations of these poles and zeros, that may change. Let's look at one more possibility. Suppose now that we start with 3 poles and 2 are complex. Now what we want to do is say, what's the gain to get us to that point? And let's just assume, for illustration purposes, that to get us to the unit circle on the right has not yet pushed the pole on the real line to the left of -1. So that's now the lower, that would now be the upper bound of stability. We would start at 0, and so now our k for stability would be between 0 and, let's say, k1. Let's say this is now the k1 value, And we might now also see that the value there might push us out here, but we're already unstable. And so let's say that this is now the gain we're calling case of 2. We would now see that case of 2 is actually going to be bigger than case of 1. Or it could turn out that you now have the value to get you to -1 might actually be the lower bound on stability, and your triangle location, which now might be what pushes you here to the boundary, might be beyond the unit circle. So here, the stability again would be lower bounded by by 0, but then the upper limit would be bounded by this square. And in this case, if we call this particular value again case of 2, and maybe maybe let me label those with the symbols, and then it won't be so confusing. Let's say that that's now the k square, and this is k triangle. In this case, we have k triangle being bigger than k square. And hopefully that now gives you a feel for how you can select the range of k for stability, and it depends obviously on the pole zero pattern that you begin with. Once you have that pole zero pattern, what determines the performance of your closed loop system? And that's going to be governed by the dominant poles. Suppose we had a 5-pole system, and in this case it really doesn't matter where we have zeros or might have zeros. They don't influence stability. Let me put some in here. They would have to be in conjugate pairs. But the dominant poles are going to be, in this class, we'll assume that those are the poles that are inside the unit circle and closest to 1. That's what we will consider to be our dominant poles. If we had, let's say, all real poles, we are just going to establish the convention for this class that let's just focus on the pole, the real pole closest to z equal 1, and we'll just determine our performance behavior based on that single pole, real pole that's close to 1. It's not exactly true because these other poles that are inside the unit circle will help coordinate or improve or enhance the stability behavior, but let's just go ahead for ease of computation and discussion. We'll just say that if we have multiple poles, let's just focus on those that are close to 1, z equal 1 inside the unit circle. Obviously, to be talking about settling time, percent overshoot, and peak time, we have to have all of our poles inside the unit circle. But once we now have our poles inside the unit circle, let's say we have this particular case, the gain k could be adjusted to get us to the square, or it could be increased to get us to the triangle. If it gets us to the square, then we would consider, or we would determine our performance behavior, the settling time. Since it's real, we would only have to worry about the settling time based on that radius r sub 1. So our k value to get us to the square, we could say that's k equal k1, then the dominant pole would be located at r1 units from the origin. So z is equal to r1. We know our 1% settling time formula, and we can now solve that for n sub s. And we could do that without having to know the sample period. If it's real, we don't have a percent overshoot, and we have no peak time. Now, if we crank up the gain more, then we actually will have the possibility of locating our dominant poles at those triangle locations. And in that case, now we do have complex conjugate poles. We have poles at R2 theta 2 and R2 conjugate of theta 2 or minus theta 2. We could now find our performance specification, settling time, percent overshoot, and time to peak, based on a z value of a radius r2 and an angle of theta sub 2. And you can now find, using our formulas that we've had before, what is the settling time, percent overshoot, and peak time from that given information.